So, hello to everyone who is watching on YouTube. So, I'm waiting for since no one has joined the session till now, I'm waiting for a few people to join the session to get started. So, if no one joins it, like let's say for 5 minutes, I'll start discussing about today's session. So, yeah, I'll start in 5 minutes. Okay. Hello, Sambit. So, I'll start discussing about today's session in like let's say 1 or 2 minutes. Since okay, maybe I guess I can just start anyways since you have joined. So, hello, Sambit, and hello to everyone who is watching on YouTube as well. So, let me introduce myself for the last time in this course. So, yeah, I am Lakshya Saki, the discrete math problem solving TA for the Tuesday sessions. So, as you may already know, that the problem solving sessions have already finished. We have already had 12 problem solving sessions. And so today we are having our last session for this course. I'm interacting with you guys for the last time, and this is basically a summary session in which I'll be sort of summarizing, or let's say I sort of prepared a cheat sheet for the course. Let's just not say just a cheat sheet, but a list of topics which we have sort of covered in the course, and I'll be just going through that in 2 hours today. So, like, it's a brief overview of what all we have covered in this course and how far we have come. So, yeah. So maybe I'll just start with sharing my screen and I can start discussing the what all we have covered in 12 weeks. And I'll be going like week by week. So yeah, I'll just share my screen now. Okay, so I hope my screen is visible. If there are any issues, Sambit, you can tell me in chat, or like, yeah, you can type in chat if my screen is not visible or there's some issues with my audio as well. Otherwise, I'll just get started. So yeah. So as I said, so this is our 13th session. This is not exactly a problem solving session like earlier 12 sessions or problem solving sessions. This is more of a summary session where I'll be summarizing what all we have discussed in the previous 12 weeks. So yeah, so I'll just start going week by week. So in the first week, first 2 weeks were more of introductory weeks where we started off with basics of discrete mathematics. So in week one, we covered the topics related to propositional logic, logical equivalence, rules of inference, and resolution. So first of all, we started with what are propositions. So propositions, as we know, propositions are statements which are either true or false. Then there are different kinds of propositions. So we came to what's a tautology. So tautology is a proposition which is always true, regardless of the values of Boolean variables in that proposition. So for example, this proposition P or not P is a tautology, because if we take P as true, then also this statement is true, this proposition is true. If we take P as false, then also this proposition is true. So that's why it's a tautology. And then we came to so note that this is not an exhaustive list of topics which I prepared. These are just sort of the what I found to be the main highlights of what we had discussed, because it's obviously not possible to discuss in 12 hours, the in 2 hours, the whole exhaustive list of topics of the whole 12 weeks. So it's sort of, let's say, a cheat sheet or a sort of a summary for everything. So yeah. So then also we covered what are satisfiable expressions. So what are satisfiable expressions? The propositional expressions for which there exists at least one assignment of Boolean variables at which the expression is true. So note that tautology was a proposition in which, regardless of the value of Boolean variable, so for all assignments of Boolean variables, if the proposition is true, then it's a tautology. If there exists at least one assignment, like not all assignments, but we just need one assignment to be true, then that expression is called a satisfiable expression. So yeah. And then we covered different rules of inference in the lectures. And then there was the principle of resolution, which was discussed. So yeah, so this was the first week. Then came the second week, which was basically continuation of logic only. But now, but here we started with predicate logic. So predicate logic and proof strategies. So what was predicate logic? So predicate logic was a basic propositional logic along with the expressions like for all and there exists and stuff like that. So when there are quantifiable operators associated, so that's called the first order predicate logic, where we also have operators like for all, there exists, and stuff like that. So we covered what is predicate logic, and then there were rules of inference in predicate logic, and then finally there was a discussion about different sorts of proof strategies, like how do we prove stuff. Like discrete maths course generally starts off with understanding how to prove stuff. So yeah, how to basically formally prove things to make sure that we don't make any mistake in the proof. So proof strategies were discussed, like proof by contradiction. So proof by contradiction is strategy in which we assume what we have. Suppose we have to disprove something. So we assume that the statement is true. and then we arrive at a contradiction. And so the statement should have been actually false. So that's how proof by contradiction works. And then we also discuss like proof by mathematical induction, to the principle of mathematical induction, basically. So yeah, this is covered in high school as well. So I guess everyone knows what mathematical induction is. So yeah. And then after these 2 weeks, these were sort of preliminaries. Then we started off with some of this stuff of discrete maths. So in week three was more about sets and relations. And in sets and relations, so first of all, what is a set? So a set is a collection. So a set is just defined as a very basic term, which is a collection of well-defined objects. So this well-defined objects is a very vague term, but yeah, bear with me, I guess. The set is a collection of objects. You can define a set over any objects. So yeah. And what does well defined mean? Well, the object should be like we should be able to write about that object mathematically. Like that's why we are saying something like well defined, because inherently we are discussing maths only. So the object should be we should be able to define the object mathematically as well. So yeah. So this object can also be a set. So a set can be a collection of sets also and stuff like that. For example, a power set is also a set which is a collection of sets only. So a power set of a set S is nothing but a set which contains all the subsets of S. Uh, and the cardinality of power set of S is nothing but 2 raised to the power cardinality of S. So this mod S symbol is nothing but cardinality, and cardinality means the number of elements or number of objects in that set. And how do we show this? This is easy to show because for any subset, uh, an element of the set can be present in that subset or absent in that subset. So there are two choices for every element, and there are mod S elements because there are like this is how mod S is defined. So 2 raised to power mod S is the number of possible subsets, and that's how we get cardinality of power set is 2 raised to the power mod S. Then we came to relations. What are relations? So a relation over the sets A and B is nothing but a subset of the set A cross B. So this A cross B has also been discussed in the lectures. What does this mean? So basically, we take ordered pairs among A and B, where first element is from set A and second element is from set B. So yeah. So a relation is nothing but a subset of this set A cross B. And then we covered like what is matrix multiplication, matrix representation of a relation. So what does it mean by matrix representation of a relation over a set S? So whenever you define a relation over a set S, it essentially means we are defining the relation as a subset of the set S cross S. So here we define the relation as a subset of A cross B. But if we are defining a relation over set S, it just means that note that we need two sets to define a relation A and B. But here, if we want to say that if we just want to write over a set S, it's just short form for saying that relation is defined over the set S cross S. So if A is equal to S and B equal to S, then we say that relation is defined over a set S. So yeah. So we came to this matrix representation of a relation. And what's this matrix representation? So a matrix in which I comma jth entry of the matrix is 1 if and only if I comma jth elements of set S are related in R. So if ith and jth elements of set S are related by the relation R, then we set this matrix entry to 1, else we set the entry to 0. So else 0. So yeah. So what does this mean? So in other words, let's say we just order the elements of the set S by this A1, A2, A3 till AN. Then the matrix representation of relation R is an n cross n matrix because there are n elements in the set, and it's a 0, 1 matrix. So some entries will be 0 and some entries will be 1. And what entries are 1? I comma jth entry is 1 if and only if AI is related to AJ. So AI comma AJ. So if AI comma AJ belongs to R, we can also say that AI is related to AJ. So these two terms we can use interchangeably. So if AI comma AJ belongs to R, then we set I comma jth entry to 1, else we set it to 0. So yeah. So this is what we call the matrix representation of a relation. Maybe I should put this in. subscripts and superscripts to make it easier to read. So yeah. So after this, we define some operations on relation. Different types of operations are possible on relations, like composition over relations, closure, etc., etc. So yeah. And then there were some definitions like these three are like there are more definitions on relations, but these three are most important. Like personally, what I find most important are these three definitions. So what's a reflexive relation? A reflexive relation is a relation in which uh, all the elements of the form a comma a are part of that relation. So let's say we are defining the relation over a set a, then every element of this capital A set, every element small a of this capital A set uh, should be present in the relation in the form of a comma a. So every element. So basically, what does this mean? This essentially means that every element of the set should be related to itself. Then we call that relation to be a reflexive relation. Similarly, there's another definition which is symmetric relation. So what's a symmetric relation? If A comma B belongs to R, then B comma A belongs to R. So essentially it means if A is related to B, then B should also be related to A. So then we call it a symmetric relation. Similarly, what's a transitive relation? A transitive relation is a relation in which if A comma B belongs to R and B comma C belongs to R, then A comma C belongs to R. So what does this mean? If A is related to B and B is related to C, so we can take out this common element B and instead write that A is related to C also. So this is the definition of a transitive relation. And then we discussed how to. So note that there are a lot of other definitions among relations, like what is antisymmetric relation, what is like, yeah, there are a lot of other types of relations defined, but these three I find personally to be most useful. And why are these most useful? We'll come that to that next. But yeah, so and after that we covered like what's a transit, what does it mean to be transitive closure of a relation, and how do we compute these transitive closure. So remember that we could compute these transitive closures of a relation using the Floyd-Warshall algorithm. So this has also been covered in the lectures, so you can take a look at it if you want. So then we come to in the fourth week, we discussed about equivalence relations, partitions, and functions. So first of all, what's an equivalence relation? Equivalence relation is a relation which is symmetric, transitive, and reflexive. So these three terms: reflexive, symmetric, and transitive. So if a relation satisfies all these three properties, then we call it an equivalence relation. So, and equivalence relations, like just trust me, equivalence relations are used heavily in computer science. Like they are one of the central pillars of computer science. So that's why I said that like equivalence relations are very important. And since equivalence relations are defined by reflexive, symmetric, and transitive, so naturally these three relations are also very important to us. So yeah, that's why uh, I said that these three definitions are at least very important in terms of discrete maths or computer science in general. So yeah. So then we come about posets. So what are posets? Posets is short for partially ordered set. So intuitively, partially ordered set is nothing but a set which is partially ordered. And what does partially ordered mean? That all elements are maybe not comparable or stuff like that. But like a proper definition for it is like a partially ordered set is basically a set S, and it also has a relation. Oh, and also we have a relation over this set S. So this S comma R pair is a partially ordered set if like first of all, this is a notation, like this S comma R is a notation where S is a set of elements and R is a relation on S. So a partially ordered set S is denoted by two terms. First of all, a set of elements, and then a relation on those set of elements. So yeah, and a partially ordered set, and we call this sort of pair a partially ordered set only if uh, R is reflexive, antisymmetric, and transitive. So essentially, the relation R, which is defined over this set S, should satisfy these three properties. It should be reflexive. So reflexive, we know that every element should be related to itself. It should be transitive. Transitive, we know that if A is related to B and B is related to C, then A should be related to C. And it should also be antisymmetric. So antisymmetric is something whose definition I have not written here. I have written what is symmetric relation. So you can think that antisymmetric is something which is opposite of a symmetric relation. So what does antisymmetric mean? Antisymmetric just so if a symmetric relation is a relation in which if A comma B belongs to R, if A is related to B, then B is related to A. So this is the definition of symmetric relation. And what is an antisymmetric relation? Antisymmetric relation is just that if A is related to B, then B should not be related to A. So this is what we call an antisymmetric relation. If A is related to B, then B should not be related to A. In symmetric, we have B should be related to A, but in antisymmetric, we have B is not related to A. So if R satisfies these three properties, then we said that this S comma R is a partially ordered set. And yeah. So and there are some cool properties of a partially ordered set. One of those properties is topological ordering. So what's a topological ordering for a post set S comma R? So what topological ordering is nothing but an ordering of elements of the set S such that for any two distinct elements E1 comma E2 in the set S, if E1 is related to E2, then E1 comes before E2 in the topological ordering. So what does this mean? Suppose topological ordering is nothing but an ordering of elements. So ordering is nothing but laying down the elements uh, in a row. Let's say like we write the elements like suppose there are three elements 1, 2, 3, 4, 5. I write them in a line like 1, 2, 3, 4, 5 or any other order. Another ordering is like 3, 5, 4, 2, 1. So an ordering is a topological ordering. If we take that if and only if it satisfies this condition that for any two distinct elements of the set S, if E1 is related to E2, then E1 should come before E2 in the topological ordering. So for example, let's say we have the numbers 1, 2, 3, 4, 5. So one and I say the relation is defined by less than relation. So one is less than two, so one is related to two. Similarly, one is less than three, one is related to three. Two is less than three, so two is related to three, and so on. So the ordering 1, 2, 3, 4, 5 is a topological ordering there. Because for any two elements, let's say one, for example, let's say 1 and 3, 1 comes before 3 in the topological ordering, and 1 is also related to 3. But note that an ordering which is 5, 4, 3, 2, 1 won't be a topological ordering with respect to the less than relation, because 5 comes before 4, but 4 is related to 5 and 5 is not related to 4 because 5 is greater than 4 and not less than 4. So something like that. I'm not writing this down because all of this has sort of been covered in the lecture. I just want to remind you guys about this. So yeah. So this is what we call topological ordering. Then we define something like a greatest element in a poset. So what is definition of greatest element of a poset? So an element X is the greatest slash maximum element of the poset if for all elements Y which are not equal to X. So basically for all other elements, all elements other than X, X should be related by those elements. So basically every other element of the set should be related to X. And that's when we say that X is the greatest slash maximum element. So intuitively, X is the maximum element if all elements other than X are related to X. So something like this. So note that one thing to note here is that a greatest element for a poset will always be unique. And why is that? Because suppose X1 is the greatest element. Suppose X is the greatest element. Then all other elements are related to X. So essentially, since poset is defined as to be an antisymmetric set, So if all elements are related to X, that means X is not related to any other element. So no other element can be the maximum element. So there is a unique maximum. But also note that uh, it need not always exist. A greatest element does not always exist. But if it exists, because like for all elements y not equal to x, it might not be that y is related to x. So a unique element or a greatest element does not always exist in a poset, but if it exists, it is unique. So maybe I should write this down also. Note that greatest note that the greatest element need not always exist in a poset. But if it exists, it is unique. So I hope everyone is able to see why is this. I will not spend much more time on this. So then we come to what is total ordering. So earlier we defined something like a poset, so which was partially ordered set. So in partially ordered set, we need not always have for two elements, one must be related to other or other like x1 comma x2, x2 should not be related. There can be a case that x1 is not related to x2 and x2 is not related to x1. But how do we find total ordering? So a total ordering is basically a poset S comma R, where R is a total ordering if for all elements X and Y in S. So for any pair of elements, either X is related to Y or Y is related to X. So note that this is an either or. One of these should be true. Either X is related to Y or Y is related to X. We cannot have both of these as true because a poset, because we have defined it to be a poset. And in poset, a poset is always antisymmetric. And antisymmetry is defined as if X is related to Y, then Y can't be related to X. Similarly, if Y is related to X, then X can't be related to Y. So yeah. So this is how we define a total ordering. So, uh, so note that since in total ordering, we always have a pair of elements. Since all elements are always comparable to each other, so note that in a total ordering, a maximum element always exists. Note that a maximum element always exists in a total ordering. So yeah. So this is basically uh, one definition. And now we come to another definition, which was the maximal element in a poset. So a maximal element in a poset. So maximal element in a poset is defined as like an element X is a maximal element in the poset S comma R if there does not exist any Y which is other than X such that X is related to Y. So what does it essentially mean? So intuitively it means that X is a maximal element if X is not related to any other element. So this was the mathematical definition, but intuitively you can just remember it like this, that X is a maximal element in a poset if X is not related to any other element. So note that note that there can be in a poset, there can be multiple maximal elements. Note that there can be multiple maximal elements in a poset. But in a total ordering, there will always be a unique, but let's just keep it at that. Maybe just like it right like this. So note that there can be multiple maximal elements in a poset. And if a maximum element in the poset exists, if this greatest element exists, then it is also a maximal element. Uh-huh. Or maybe I should not write this, but yeah, this is, I think, sufficient that there can be multiple maximal elements in a poset. So yeah. And then, like I discussed, so this was equivalence relations, partitions, and then functions. So after this, we come to what are functions. So functions are nothing but functions are essentially relations where every element of the domain is related to exactly one element of codomain. So, so this is definition of function, and this sort of definition we have seen in high school also. So this definition is sort of easy for us. So then comes the definition of one and onto functions. So one functions which are also called injective functions. So what's a one function? So one function is a function if so basically a function f is a one function if this condition holds true. And what is this condition? Like if f of a is equal to f of a prime, then a should be equal to a prime. So just this condition is essential for a function being called a one function. And you can see what does this intuitively mean. So intuitively, this means that uh, one value of codomain is uniquely mapped by one value of domain. Either it is not mapped or it is uniquely mapped. Like no two values of domain can point to the same value in the codomain for a function to be one. And similarly, what's an onto function? So an onto function is a function if every element of codomain is mapped by some element of the domain. So these an onto function is also called a surjective function. So these definitions have also been covered in lectures as well as in our high school maths. So yeah. And then what's an invertible function? So invertible function is a function which is one as well as onto. So a function is invertible if and only if it is one as well as onto. And what is an invertible function? Basically, the inverse of that function exists, then that function is called an invertible function. Then we come to some properties of oneness and onto-ness of the functions. So let's say we define a function from the set A to set B. So essentially A is the domain and B is the codomain. And let's just assume for now that A and B are finite sets. So then we have a bunch of properties for these functions. So properties like so first property says that, let's say if f is one function, so basically if f is injective, then we can essentially say that cardinality of A is less than equal to cardinality of B, cardinality of set B. Similarly, if f is an onto function, then cardinality of set A is greater than equal to cardinality of set B. And if f is a bijective function, and what's a bijective function? A bijective function is a function which is one as well as onto. So essentially an invertible function. Invertible and bijective function are essentially same thing. So a function is bijective. Uh, if a function is bijective, then it means that it is one as well as onto. So if it was one, then cardinality of A is less than equal to cardinality of B. If it was onto, cardinality of A is greater than equal to cardinality of B. So the only combo in which both of these things can happen is when cardinality of A is actually equal to cardinality of B. So yeah. So if F is bijective, then cardinality of A is equal to cardinality of B. So yeah. So after this, we come to another property which says that if I'll just come back in a minute, guys. I'll just come back in a minute. Okay, sorry for that, guys. So we are at this fourth property which says that if f is a one function and cardinality of A is equal to cardinality of B, then f is also bijective. So essentially, if f is one and cardinality of A is equal to cardinality of B, then we can by default say that f is also onto. So note that here it does not say anything about onto-ness, but we can directly say that f is onto also, and so f is bijective. So this is also an important good property to keep in mind. All of this can be proven easily, but consider this as sort of a cheat sheet or some things which you should be able to see directly instead of deriving it every time. So yeah. And then there's this fifth property which says that if f is an onto function, so fourth property was if f is one and cardinality of A is equal to cardinality of B. The fifth property says that if f is onto and cardinality of A is equal to cardinality of B, then also f is bijective. So essentially, if f is onto and this condition holds, then f is a 1-1 function. So, which essentially means that f is a bijective function. So yeah. So, and furthermore, there were a few more properties related to compositions of functions. So there was this property like, so consider a function GOF. So this GOF is a notation for composition of function. So I'm assuming everyone is familiar with this notation and what is composition of functions. So consider a function h, which is basically G composed over f, where f and g are functions such that f is from set A to set B and g is from set B to set C. So note that this h function is composed like GOF. So essentially the range of f and the domain of G should match. That's the condition on which that's the condition when we can compose a function G over f. So what essentially means is that this B and B will cancel out and something like h will be a function from A over C, because h will take a input in the function h, will be giving first an input to the function f, and f takes an input from set A, and this input from set f will give an output to in the set B, and this output in the set B will be an input to this function g. So this should also be from the set B itself. And after this function g will give us a final value, which will be from the set C. So that's why h gives a value from the set C. So that's why h is a function from set A to set C. And there are some properties for h also. Like, so if this composition is 1-1, then the initial function f will also be 1-1. And if this composition is onto, then the function g is onto. These are also two properties related to composition of functions. So yeah. So this concludes the week 4. And then came week 5. And in week 5 was primarily about theory of countability. So what are countable sets and what are uncountable sets and whatnot. So yeah. So a brief summary is that so there are two types of sets, finite sets as well as infinite sets. What are finite sets? Finite sets are sets which have bounded cardinality. Infinite sets have unbounded cardinality. So I note that this distinction does not just stop here, this division. And so now we further divide these infinite sets into two types of infinite sets. So there are two types of infinite sets, countably infinite and uncountably infinite. So what are countably infinite set? So a set S is countably infinite if and only if S has unbounded cardinality. So first of all, since it's infinite, it should have unbounded cardinality. But why is it countable? It is countable because it should have a bijection with Z plus. And what's this? What does this symbol Z plus mean? I hope everyone is familiar with these sort of notations by now, that Z plus means the set of positive integers. So basically, a set S is countably infinite if and only if S has unbounded cardinality and it has a bijection with Z plus. So Z plus is a set of positive integers. So if a set S and this Z plus have a bijection, so basically there exists a function f which is 1-1 as well as onto, such that Z plus is the domain and this set S is the codomain, then we can say that the set S is countably infinite. So then there were some properties like, so this is countably infinite sets, and for sets for which this property does not hold, uh, like if there does not exist any bijection with Z plus for a set S, then we'll say that that set is uncountably infinite. So yeah. And then this property is like some properties over when sets are countably infinite and when are they not. So something like if A and B are countably infinite sets, then A cross B is also countably infinite. So these sorts of properties I also discussed in the original problem solving sessions which I took. But so I'll not be discussing the proofs for these or anything by now. So I'll just be discussing these properties. But you can see like why these will hold true intuitively also. And then there was this property that a set of finite subsets of countably infinite set is also countable. So what does this mean? So yeah, this statement seems to be a bit confusing, but let me just break it down. So the set of finite subsets of a countably infinite set. So if we start off with a countably infinite set and we take all the finite subsets of that set, let's say this countably infinite set was set S. If we take a set of all the finite subset of S. So what are finite subsets? The subsets which are bounded by some size. The size of those subsets are bounded by some integer. So the set of finite subset, this is the set of finite subsets of S. This set is also countable. So whenever this S is countable, then the set of finite subsets of S is also countable. Similarly, another property is that the power set of a countably infinite set is uncountable. And how do we show this? Why is this power set of a countably infinite set uncountable? The proof for this is done using Cantor's diagonalization argument, which was also discussed in the lectures. So yeah, this is a very niche argument and like pretty interesting. So yeah. So maybe I should put this here only. Uh, yeah. So, and then there was this property that union of countable number of countably infinite sets is countable. Another confusing property, but let me just break it down. So we are taking union of some sets. So we are taking union of countable number of countably infinite sets. So basically we are taking some countable infinite sets like sets S1. Suppose S1 is countably infinite, S2 is countably infinite till some set Sn. And these all are countably infinite sets. And there's this union, we are taking union over all of these. So let's just say this n goes to infinity also. So even if n is very large, the union of all these countably infinite sets will also be countable. So this is another property. And then there was this discussion about Cantor's diagonalization argument, like which has very nice proof. And from this, we were able to show that the power set of a countably infinite set is actually uncountable. So what's a power set? Power set is the set of all subsets. So note that the set of finite subsets of a countably infinite set was countable. But what is power set? Power set is nothing but again a set of subsets of a set, right? So if we start off with a countably infinite set here and countably infinite set here, here we are taking set of finite subsets and we are saying that it is countable. Here we are taking the power set, which is not the set of finite subsets, but rather set of all possible subsets. So infinite subsets will also come here in the power set. So when we include infinite subsets, then this becomes actually uncountable. If we only take the finite subsets, then it's countable. Otherwise, it is uncountable. So yeah, something like that. So note this distinction in mind. If we are taking set of finite subsets, then it's countable. If we are taking set of all subsets, which includes infinite subsets as well, then it becomes uncountable. So then there was this property that union of uncountable number of countably infinite sets can be uncountable. So if we take countably infinite sets, a lot of countably infinite sets, an uncountable number of countably infinite sets, then their union can be uncountable. Note that important word is here can be. So it can be uncountable, but there exist instances where this is countable also. And I discussed one such example in the problem solving session also. So you can take a look at that also. So yeah. And then there was this property about uncomputable functions. And like this was not too hard to see. So yeah. Then came week 6, which was about combinatorics. Sorry for that, guys. Somehow my mic got muted actually, and like yeah, there was some trouble with Teams. So yeah, so I was just discussing this week six. So week six was about combinatorics. So week six started off with combinatorics. So in combinatorics, we started off with first of all, what are permutations? So permutation is nothing but, and it is denoted by NPR, and it denotes the number of ways in which art items can be selected and then ordered out of n items. So note that how do we define a permutation? So we are given n items. Out of those n items, we first select our items and then order them. So basically, uh, we select our items and then we can also order those items. And this is how we define permutation. And the formula for that is given by n factorial divided by n minus r factorial. And similarly, we define what are combinations. Combinations are denoted by n choose r and cr. I like to call this n choose r. And it is defined by number of ways in which r items can be selected out of n item. So, and the formula for this is n factorial divided by r factorial times n minus r factorial. So note the difference between permutations and combinations. So in combinations, we are just finding number of ways in which r items can be selected. So if we just assume this formula to be true, that to select r items out of n items, we can do it in these number of ways: n factorial by r factorial times n minus r factorial. And what are permutations? Here we are selecting and then ordering them also. So first we select those r items in this n factorial by r factorial n minus r factorial number of ways, and then order these items. And since we have r items, so r items can be ordered in r factorial ways. So that's why to find out the number of permutations, we just find out number of combinations and multiply it by r factorial. As you can see, if we multiply this quantity by r factorial, we'll just obtain this quantity, which was the formula for permutations. So yeah. So this is how we arrive at the formula for combinations and permutations. And then there was discussion about counting using recurrence relations. So yeah, like there was discussion about Fibonacci sequence and stuff like that. So yeah, and then we came to how to solve actually linear homogeneous recurrence equation. So if you guys remember, how do we do this? We replace the t nth term by x raised to power n, t of n minus 1 by x raised to power n minus 1, x raised to power n minus 2, and so on, and then solve the equation which forms, and then like find out the roots of that equation. And like let's say alpha and beta are the roots, then the solution is given by c1 alpha to the power n plus c2 beta to the power n, and then we find out the coefficient c1, c2, and so on. So I'm not writing this down, but I'm just telling, like saying this orally because all of this is already been discussed in the lectures. So yeah. Then came week 7, which was again a continuation of combinatorics only. So moving on from this, so in week 6, in the last, there was discussion about solving linear homogeneous recurrence relations. And then this extended to how do we solve linear non-homogeneous recurrence relations. What are homogeneous recurrence relations? What are non-homogeneous? And all of this has been discussed in the lectures. So yeah. Then there was this definition about a very important number in combinatorics, which is the Catalan number, which basically gives us the number of ways of going from bottom left to top right of an n cross n square grid by moving only one step right or one step at a time, one step up at a time, without crossing the diagonal of the square. So we are given essentially a square, n cross n square. We can move at any time. We can move one step right or one step up. And the only condition is that we cannot cross the diagonal of the square, and we need to move from bottom left to top right. So number of ways for this is given by 1 upon n plus 1 times 2n choose n, which is essentially 2n choose n minus 2n choose n minus 1. So yeah, so how do we arrive at this formula? The derivation has been discussed in the lectures. So you can arrive at this. Yeah, so you can see the lecture if you want to find out the derivation. But yeah, so this is how we define Catalan number. And then came the principle of inclusion exclusion. And the basic idea behind principle of inclusion exclusion was something like this: that suppose we have three sets A, B, and C. then the cardinality of A union B union C is nothing but A plus B, cardinality of A plus cardinal. Maybe I should put these two in these arrows. So yeah, cardinality of A union B union C is given by A plus B plus C minus cardinality of A intersection B minus B intersection C minus C intersection A plus A intersection B intersection C. So essentially, cardinality of union is given by summation of cardinalities taken one at a time minus summation of cardinalities taken two at a time, their intersections, plus taken intersections taken three at a time. Similarly, this sort of inclusion exclusion extends to this sort of thing also. Suppose instead of finding out A union B union C's union, we want to find out A union B union C's intersection. So you can just replace all the intersections by unions and unions by intersection. And you can see, verify this yourself using Venn diagrams that these formulas work out. So yeah. So this is the basic idea behind principle of inclusion exclusion. So note that here we only had 3 sets, but this can be generalized to n sets also by a similar concept that we take sets 1 at a time, then 2 at a time, 3 at a time with alternating signs. So yeah, something like this. Then we define what are derangements. So our derangements are nothing but permutations of n numbers from 1 to n, in which ith number does not go to ith place for all I. So for all positions 1 to n, like if we are talking about second position, the number 2 should not be present on the second position. Similarly, number 3 should not be present on the third position, and so on. So these sorts of permutations are called derangements. And then we sort of use principle of inclusion exclusion to find out number of like this number of derangements we were able to find out using principle of inclusion exclusion. Similarly, we were also able to count number of possible onto functions. So let's say we are given two sets A and B, and we want to find out number of possible onto functions from set A to set B. We can do this using principle of inclusion exclusion also, and some other stuff. So yeah. So basically, principle of inclusion exclusion also has a lot of uses. And after this came week 8, and in week 8, we discussed graph theory. We discussed about graph theory, and it started off with defining what's a matching. So matching is nothing but a subset of edges of a graph G, such that no two edges of the subset share a common vertex. So yeah. And now what's a complete matching? A matching in a graph G is a complete matching if it matches all the vertices in G. So yeah. So if all the vertices of G are matched, then we call it a complete matching, and otherwise it's an incomplete matching. And then there was this Hall's marriage theorem, which essentially quantified, like in a bipartite graph, when will a complete matching exist. So this Hall's marriage theorem quantified when will a complete matching exist and when will it not exist. So you can see the lectures if you want to see what does Hall's marriage theorem state. But it was a very cool theorem, and its proof was also very nice. So yeah, this was a very nice theorem. And then there was definition of maximal matching. What's a maximal matching? A maximal matching is a matching in which no further edge can be added to increase the size of the matching. So yeah. And then what's an edge connectivity of a connected graph G? So for a connected graph G, how do you define edge connectivity for that graph? Edge connectivity is defined as the minimum size subset of edges which need to be deleted from G so that G becomes disconnected. So this is how we define edge connectivity of a connected graph. So initially graph G is connected. So now how many edges should I delete? The minimum size subset of edges which should I delete so that G becomes disconnected, and that is called the edge connectivity. Similarly, we can define vertex connectivity also. In edge connectivity, we delete subset of edges. In vertex connectivity, we delete subset of vertices. So minimum size subset of vertices which need to be deleted from G so that G becomes disconnected. So note that when we are deleting vertices, one issue which can arise is that suppose if I delete all the n vertices from the graph, then there does not exist any graph now. Everything has vanished. So that's why we sort of say that vertex connectivity is defined such that vertices deleted such that G becomes disconnected, or G contains a single vertex after deletion. So for an n vertex graph, the vertex connectivity's maximum value can be n minus 1 only, because after n minus 1 deletions, there will only remain one vertex. And after that, we can't delete further vertices. So that's why vertex connectivity of a graph G is always bounded by n minus 1 if we have n vertices. So maybe I should write this also. So vertex connectivity of a connected graph G is always bounded by n minus 1, where n is the number of vertices in G. So yeah. And then we define what's a cut edge in a connected graph G. And a G is a cut edge in G if deletion of E disconnects G. So initially G was connected. If this exists, note that a cut edge need not always exist, but we say that a cut edge exists if deletion of E disconnects G. Similarly, what's an so that's how we define a cut edge. And there was another definition which was an edge cut. So note that there is this cut edge and edge cut. These are two different terms. So don't confuse them with each other. So cut edge is nothing but an edge whose deletion disconnects G. But an edge cut is a subset of edges whose deletion disconnects G. So cut edge is a single edge cut is a subset of edges. So yeah. So keep this in mind that edge cut and cut edge are two different things. So yeah. So after this, we continued in week 9 with graph theory only, and there was definitions about what's an Euler path. So a Euler path is a essentially essentially an Euler path is a path which visits all edges exactly once. So note that these Euler path, Hamiltonian path, stuff like this need not always exist in a graph. So, but if they exist, like how do we define those paths? So yeah. Note that Euler path and Hamiltonian path need not always exist, but they are defined like this, that an Euler path is a path which visits all edges exactly once. So yeah. And similarly, what's a Hamiltonian path? It's a path which visits all vertices exactly once. So Euler covers all edges, Hamiltonian covers all vertices, and both cover exactly once. So yeah. So note that these not always exist in a graph, but still these are very important definitions for other purposes. So yeah. So then we have a quantification of when a graph contains an Euler path and when does it not. So a graph has an Euler path if and only if there are there was this theorem in the lectures that a graph has an Euler path if and only if there are exactly two vertices with odd degree in it. So if all other vertices are even degreed and only two vertices have exactly odd degree, then we can actually say that the graph is an Euler path. Essentially, for only these sorts of graphs, a path exists which visits all edges exactly once. So yeah. And then we define an Eulerian graph. So note that there was this Euler path, but there is something else which is Euler circuit or like which has been discussed in the lectures as well. And if a Euler, so basically you can just see that there's another definition which is an Eulerian graph. So this Euler path and Eulerian graph are two different terms. So don't confuse them with each other. So a graph is Eulerian if and only if all vertices have an even degree. So note that a graph had an Euler path if and only if there were exactly two vertices with odd degree. But if all vertices have even degree, then we say the graph is Eulerian. And what's essentially an Eulerian graph? It's just a graph which contains an Euler circuit, not an Euler path, but rather an Euler circuit. And what's the difference between a path and a circuit? So a path does not repeat edges. In a circuit, basically the starting and end point of the starting and end point should be the same. That's when we call it a circuit. So essentially, these definitions are available in lectures also. You can see there also, but I'm just covering main stuff. So yeah. A graph is Eulerian if and only if all vertices have an even degree. Then there were discussions about vertex and edge coloring of a graph. So how do we define vertex coloring and how do we define edge coloring for a graph? So yeah. And in any graph G, the edge chromatic number, basically the number of colors needed so that any two adjacent edges have different colors. So is actually greater than equal to maximum degree of a vertex in G. So the edge chromatic number is always greater than equal to maximum degree vertex in G. So something like this. So you can see why is this true. I discussed this in problem solving sessions also. You can see what are these vertex and edge colorings also. These has been discussed in the lecture. So yeah. So maybe just to define what were these vertex and edge colorings without typing them down. So what's a vertex coloring? So vertex coloring is essentially we color all the vertices such that no two adjacent vertices. How do you define adjacent vertices? Vertices which have an edge between them. So if no two adjacent vertices have the same color, then we can say that is a valid vertex coloring. And similarly, how do you define an edge coloring? We color the edges by different colors such that any two adjacent edges, so essentially the edges which share a vertex, they should have different colors. And that's when we say that it's a valid edge coloring. So something like that. So edge chromatic number is nothing but the number of colors used in that edge coloring. So the edge chromatic number for any edge coloring is always greater than equal to maximum degree of a vertex. So this is what this statement says. So yeah, something like this. And then after this, in this week 10, we came to number theory. We started talking about number theory. And in number theory, there we first of all talked about GCD. GCD is nothing but greatest common divisor. We know about it from high school also. And we talked about Euclid's division algorithm to extended division algorithm to find the GCD of two numbers. So yeah. And then in regards to this only, there was a Bezout's theorem which said that if GCD of so if for two numbers x comma y, there exists coefficient a and b such that ax plus by is equal to GCD of x comma y. So you can see the exact statement in the lectures. So essentially there was this Bezout's theorem and there were the coefficients defined as like Bezout's coefficients also. So there was some problems related to this Bezout's theorem and Bezout's coefficients in one of the problem sessions also, which I held. So you can look at the 10th problem solving session. There I discussed about this also. So yeah. And then coming back to number theory, so there were some straightforward results like which you should know by heart. Like yeah. So if A is mod A is like congruent to B mod n, so this symbol I represent it as congruency symbol. This symbol refers to congruency symbol. So note that I do not have like three horizontal congruent symbol on my keyboard. So that's why I represent congruence by this. So if A is congruent to B mod n, then essentially A raised to the power k will also be congruent to B raised to the power k mod n. So yeah, something like this. So this is a very important property which is used a lot of time in number theory. And then there came this Fermat's little theorem, which said that for any prime number p and an integer a such that GCD of a comma p is 1. So note that p is prime. So the only numbers for which GCD of a comma p is not equal to 1 will be multiples of p. So for n for if a is not a multiple of p, then GCD of a comma p is 1. Then we can apply this Fermat's theorem, which essentially says that a raised to the power p minus 1 is congruent to 1 mod p. So, and what does this mod notation essentially mean? So this means that if we divide a raised to the power p minus 1 by p, then there will be a remainder of 1 left. Or essentially like saying something like a raised to the power p minus 1 is divisible by p. So something like this. So I hope everyone already knows what a congruent symbol is. Then after this, there were some discussions about primality testing. So how can we test whether a number is prime or not, a prime or composite? So, essentially the main idea was to use this Fermat's little theorem to find out if a number is prime or not. And then there were these Carmichael numbers, which were essentially so the primality testing technique which we discussed. Carmichael numbers were the numbers which essentially were composite but they would fail our primality tests also. So essentially, if we use a certain type of primality test, Carmichael numbers, even though being composite, they would come out as prime in that primality test. So yeah, something like that. This was also covered in the lectures. So yeah, you can take a look at the lectures, what are actually Carmichael numbers, their exact characterization and stuff. And what was this test also. So yeah. So then after this came the 11th week, and in 11th week we started off with abstract algebra. So number theory was limited to just 1 week, and from 11th week we came to abstract algebra now. So just word for the caution for the future, like in future courses also. So abstract algebra initially seems a bit difficult and very like overflowing with a lot of notations and stuff. But once you get comfortable with notations, and believe me, like it is not that messy as it seems to be at start. Because generally in abstract algebra, there are a lot of symbols and notations which you have to get familiar with in the start. That there are a lot of definitions. But once you get comfortable with all of that, then a lot of things actually start to make sense and become sort of intuitive. So yeah, the first the biggest hurdle in starting off or understanding abstract algebra is the start itself. So don't get discouraged by looking at abstract algebra and a bunch of definitions. Just go through them and try to understand them. And once you're comfortable with them, trust me, it will become a lot easier. So yeah. So we started off in the week 11 with abstract algebra. And so in abstract algebra, there are different kinds of things defined. So first of all, we started off with group theory in week 11. So in group theory, there was the definition for a group. So, so essentially a group is defined by two things. Uh, a group G is defined by a set of elements G and an operator associated over this set G. So this O is an operator over the elements of set G, and O is a binary operator. Basically, it takes two operands, one on the left and one on the right. So a group G is essentially a set G of elements with the operation O defined over these elements, such that the four properties hold. So a group G comma O is essentially a group when these four properties hold. So a group has these four properties. And what are these four properties? These four properties you should remember like this is sort of a definition. So there is no understanding there's no understanding part like why these four properties, but yeah, just keep in mind that for a group, these four properties should be there. So first property is closure. And what do you mean by closure property? That for any two elements A, comma B in G, these A, comma B can be equal also, can be unequal also. So for any pair of elements A, comma B in G, A O B should also belong to G. So note that this is an operator, right? This O is an operator. So it takes two inputs and gives an output. So if A and B are inputs, then AOB is an output, and this should also belong to G. So this is what we call the closure property. So this should hold true. Then associativity should hold true. This is something which we know from high school also. What is associativity? So for any three elements A, B, C in G, A of B of C. So for if we first calculate B of C and then calculate A of the output of B of C, then it should be actually equal to the output of first computing AOB and then like computing AOB's output with C. So something like that. So so associativity just means that order of computation should not matter if we are taking three terms. That if we take BOC first or if we take AOB first, it should not matter. That's what associativity says. Similarly, now there was this third property which says existence of an identity element. So for something to be called a group, there should exist an identity element. And what's the definition for an identity element? So there should exist an element E in G such that for any element A in the group G, AOE should actually be equal to EOA, and this should actually be equal to A itself. So basically, there should exist one element E such that for any element of A of group G, AOE should actually be equal to EOA, which should be A itself. So suppose let's say the operation was addition, then 0 is an identity element because 0 plus anything is equal to that number itself. So 0 plus a number is equal to that number itself. So that's why 0 is an additive identity because it's an identity over addition. So then this E is called the additive identity element of the group. So 0 is the 0 is additive identity, is an identity over addition. Similarly, 1 is an identity over multiplication because 1 multiplied by a number n gives back the number n itself. So something like that. So you can think of it in terms of addition or multiplication also. But yeah, it is in general for general groups. And the fourth property which should hold true for groups is invertibility. And what's an invertibility? Invertibility is that for any element A in the group G, there should exist an element B such that AOB should be equal to BOA, which should actually be equal to E, where E was the identity element of the group. And this B is called the inverse of element A. So note that for every element of the group, the inverse of that element will change. Like let's say over addition, inverse of 2 is -2 because 2 plus -2 gives 0. Similarly, for 3, inverse of additive inverse of 3 is -3. Similarly, multiplicative inverse of 3 is 1 by 3 and stuff like that. And it is denoted, inverse is generally denoted by a raised to power -1. So note that this a raised to power, this a need not be a real number. Like since this is abstract algebra, this group G can be anything. So this is a raised to power -1 is just a notation for inverse. So don't think of it as 1 by a, just think of it as an inverse over the group. So yeah. So if these four properties hold, then we call it a group. And now we come to what are abelian groups. So an abelian group is a group which also has, so it is a group. So first of all, it should have all these four properties. But if it also has the commutative property, and what's the commutative property? That for any two elements A, comma B, AOB should be equal to BOA. So if a group has this commutative property also that AOB is equal to BOA, then it's called an abelian group. So note that you can see that abelian groups are somewhat nicer than general groups because like AOB, we can replace AOB by BOA also. So something like that. So yeah, the groups do not have this commutative property, but abelian groups have. And sometimes this makes our life easier in certain settings. So yeah. Then there was this discussion about what a cyclic group stands for. And then there was definition about what's a subgroup. So a subgroup is a group H comma O is called a subgroup of the group G comma O if H is a subset of G. So essentially, note that it need not be a proper subset. H can be equal to G also. H just needs to be a subset of G. The only thing is that this H comma O should also form a group. So essentially, H should be a subset of G. And also this H comma O should satisfy a group property. So basically, these four properties should be satisfied by H comma O also. So G comma O was a group, so it actually satisfied. But if we take certain, so not all subsets will be subgroups. But if certain subset H comma O satisfies all these properties as well, then we call that as a subgroup of the group G. So yeah. So note that all subsets of G won't form a subgroup because these four properties for H comma O might not hold true for all, but there can exist certain subgroups. So like it is easy to see that just the group which contains the identity element forms a subgroup. And similarly, if H equal to G, then it is also a subgroup. So any group G comma O where cardinality of G is greater than equal to 2 has at least two subgroups, which are when H is equal to identity element and when H equal to G. And there can be further more subgroups also. So something like this. So I've discussed these things in problem solving sessions also, and these other things may have been discussed in lectures also. So yeah, I'm not going to too much detail here. Yeah. Then there was this definition about what's an order of a group. So order of a group is nothing but number of elements of G. Number of elements in the group G is called the order of that group. So yeah, if there are 5 elements in this subset G, then the order of that group is 5. And then there was this Lagrange theorem, which is a very important theorem in group theory, one of the central pillars of group theory. And Lagrange theorem says that order of a subgroup H divides order of the group G. So note that what was a subgroup? Subgroup was a subset of G. So what Lagrange theorem says is that if a group H comma O is a subgroup of G comma O, so essentially if H is a subgroup of G, then order of H should divide order of G. So what it essentially means is that number of elements in H should divide number should be a divisor of number of elements of G. So something like that. So note that if it's not an if and only if condition that whenever a number of elements in H will be uh, divisor of number of elements in G, then it will be a subgroup. This is not true. But what is true is that if H is a subgroup, then number of elements of H will be a divisor of number of elements in G. So yeah, something like that. And then like here first we define what's an order of a group. There is another definition which is order of an element G of a group. So note that these are two different things. Order of a group is number of elements of group. So this is associated with a group. But there exists also an order of every individual element of a group. So this is a different definition from order of a group. Although this order word is same, but these are two completely different definitions. So what is order of a group G? Order of an element G, small g of a group G. So this order will be associated with every element. So basically every element will have a different order. So this thing will be different for different elements of the group. So for a certain element small g of the group capital G, the order of that element small g is defined as the smallest positive integer n, such that g raised to the power n is actually equal to e, where e is the identity of the group capital G. So yeah. And then there was the discussion about discrete logarithms and then applications of groups like in cryptography. Like there was discussion about Diffie-Hellman key exchange, the RSA cryptography algorithm, and stuff like that. So yeah, so groups are something which are very nice to have because uh, they have a lot of applications in real life as well. So yeah. And after this, we came to the last week, which was the session which I held yesterday. So I believe like since I had discussed this yesterday also, so I don't need to go into a lot of details. But yeah, so there was this continuation of abstract algebra. So first of all, there was a discussion about rings. So I won't go into definition of rings, fields, and stuff like that because these definitions can be seen from lectures, and I just discussed these definitions yesterday only, so I don't want to get into those again. So yeah. So so there was discussion about what are rings. So rings are again a different thing from. So first of all, in 11th week we discussed what are groups and we discussed group theory. And then in 12th week we came to different objects which are rings. These are also very valuable and somewhat of a like a restriction over rings is called fields. So fields are rings which have some more special properties, and those properties are you can again see from the lecture. So rings are generally you can think of rings as being generalization of fields. So yeah, but these fields are also very important for us because they are also used in a lot of practical applications and stuff like that. So there are these rings, then there are these fields. So in 12th weeks, we defined what are rings, then there was definition of what are fields. And then we defined something like what are polynomials over fields. So polynomials over fields are nothing but polynomials which have coefficients from a field f. So you can see what I mean here from the lectures, but essentially if the coefficients are also from the field f, then the polynomial is called as a polynomial over the field f. And then there were some discussions about finite fields and their properties. And some of the properties which were very important for us were like these properties, which I'll discuss one by one. Although there are a lot of more properties, so you can see the lectures like what are the properties for finite fields. So finite fields are nothing but fields which are like finite in size. So if number of elements, so like we define groups here. Similarly, we can define finite and infinite groups also. If this set G is finite, then we call it a finite group. If this set G is infinite, then we call it an infinite group. So same applies to fields also. So if the number of elements in the field is finite, then we call it a finite field. If the number of elements in the field is infinite, then we call it an infinite field. So yeah, nothing so new. So then we discuss what are finite fields and what are their properties. So one of the properties for one of the properties, or let's say this is just a definition. Maybe I should refer to it as a definition rather than a property. So yeah. So maybe I should. Yeah. So maybe before coming to the properties, I should define what's an irreducible polynomial over a field f. Hmm, I think this sort of makes sense. So apologies for this, guys. I was just trying to uh, make things a bit more in a bit more better order, so it's easier to understand the flow of where we are going. So we defined what are polynomials over fields, and then there is this definition of what's an irreducible polynomial over f. So f is a field here. So f is a field here. So basically over a field. So what does it mean to be an irreducible? So first of all, we define what are polynomials over a field, and what does it mean to be an irreducible polynomial over a field f. So a polynomial Px over field f is called an irreducible polynomial if there does not exist any two polynomials qx, rx over f such that Px equals to qx times rx and degree of qx and degree of rx is less than degree of Px. So what this essentially means is that if a polynomial Px is irreducible when it cannot be broken down into two simpler polynomials. And what do I mean by simpler polynomials? I mean that polynomials which have a lesser degree than the polynomial itself. So let's say this polynomial Px has a degree of like 2, then there does not exist two polynomials Qx and Rx such that degree of Q and R is less than 2. So it is either 1 or 0. Uh, and the product is Px is equals to Qx times Rx. So and Px can be written as a product. So yeah. So this is what we call an irreducible polynomial over a field f. So over the field of real numbers, you can think of a polynomial like x square plus 1 being an irreducible polynomial because x square plus 1 cannot be broken down to simpler factors. I think it's easy to see. Similarly, like the polynomial x raised to the power 4 plus 1 also cannot be broken down into simpler factors. Or maybe it can be broken down. So yeah, let's just not take x square plus 1, x to the power 4 plus 1, but let's just assume the polynomial x square plus 1. X square plus 1 cannot be broken down into simpler product of simpler polynomials. So like x square plus 1 is an irreducible polynomial over the field of real numbers. So something like that. And then we discuss some finite fields and their properties. So one of the properties is that over a field f, if f of a is 0, like if f is a polynomial over the field f, then f of a is 0 if and only if x minus a is a factor of uh, f of x. So so for value a from the field f, if f of a is 0, then x minus a is a factor of fx. A polynomial, so let's say the polynomial is fx, then if f of a is 0, then x minus a is a factor of fx. So and like it's an if and only if condition, so x minus a is a factor of fx. If this is true, then f of a is 0. So yeah, so this is one of the properties of fields. And another property which is useful in finite fields is that if there exists a 0 of the polynomial in field f, so essentially like this is not a new property, but this is rather a result which can be derived from this property only. So basically what this says is that if there exists a 0 of the polynomial in the field f, so if there exists a value a at which the polynomial's value is equal to 0. So what's 0 for polynomial? 0 for polynomial is a value at which the polynomial takes the value 0, right? So a value a at which f of a is 0 is called the 0 of the polynomial. So if there exists a 0, then the polynomial is reducible. So we define what are irreducible polynomials. So reducible polynomials are polynomials which are not irreducible. So what essentially means is that reducible polynomials are polynomials which can be broken down like this: Px equals to Qx times Rx. So we say that the polynomial, if there exists a 0, then the polynomial is reducible over f. And why is this true? Because you can see this easily, because if there is a zero of the polynomial, this means that there is a value a such that f of a is zero. And if f of a is zero, then x minus a is a factor of fx. So fx can be written as something like x minus a times qx. And x minus a, like x minus a and qx are like of lesser degree than this f of x. So that's why the polynomial is reducible over f. So note that this is only an if condition, that if there is a zero, then the polynomial is reducible. It's not an if and only if condition. So what do I mean by that? Like, just keep in mind, like I discussed this in yesterday's problem solving session also, that if polynomial is reducible, it does not mean always that there will exist a zero of the polynomial in the field f. Like a polynomial can be zero, a polynomial can be reducible, but it might be that there still does not exist a zero. So for example, maybe I should write this down. Note that it might be happen that the polynomial is reducible over f, but there does not exist a zero of the polynomial in f. So the converse of this statement is not true. That's what I'm trying to say here. That it might happen that the polynomial is reducible, but there does not exist a zero of the polynomial in f. Maybe I should write it just like this. Note that the converse of this statement might is not true. The converse of this statement. So the converse is actually saying that if polynomial is reducible, then there is a zero. So this statement is not true, and you can take an example for this. I discussed the example in lectures also, in the problem solving session also. So for example, take the polynomial. So over the field of real numbers, consider the polynomial. Hmm. So this is not a finite field. Like I said that these are finite fields and their properties, but just trust me, like I'm just discussing this over field of real numbers. Real numbers are infinite fields, but still we can find these sorts of examples over finite fields also. So yeah. So for now, I'm just writing over real numbers, but this sort of example can be found out for a case of finite fields also. So just consider this polynomial of x squared plus 1 times maybe x squared plus 1. So yeah. So f of x is equals to, maybe not like this, but rather just sit like this. So consider the polynomial f of x is equals to x squared plus 1 whole square. So it is easy to see that this polynomial f of x is of degree 4, but it can be broken down into two simpler factors qx and rx, which are x squared plus 1 and x squared plus 1 each. So qx equal to x squared plus 1 and rx equal to x squared plus 1. So this polynomial is actually a reducible polynomial, but uh, so the polynomial is reducible over f, but still there does not exist a zero of the polynomial over field f. So because x squared plus 1 whole squared does not have a real root, right? We studied this in high school also, that this quantity is always greater than zero over a set of real numbers. So this quantity does not have a real root. So even though the polynomial was reducible, this f of x was reducible, still there did not exist a zero over the field of real numbers. So that's why the converse of this statement is not true. So yeah. This is one thing to keep in mind. There was a question based on it in yesterday's session also. So yeah. And then after this, there were some applications of finite fields, which were discussed in the 12th week, which was like something like n comma t Shamir secret sharing. I discussed about this last lecture, last yesterday's problem solving session also. So this secret sharing, this Shamir secret sharing essentially says that Suppose we are given a treasure and the there are n people among which this treasure should be divided. Like suppose there is a box, like a treasure box, and there is a city of n people present. And we want to say that no single person can come and like open the treasure box and take stuff from it, but only when like t people come together, only then they should be able to uh, open the treasure box where T is chosen by us. Like, what do we want? If we want that only a group of 5 should be able to open the treasure box, only a group of 10 should be able to open the treasure box. So we can set T equal to 5 or 10 as we like. So what we essentially say is that in a city of n people, if we want that the box should open only when at least T people come together, and it should not open otherwise. So if there are less than T people coming together, then the box should not open. At least T people should come to open the box. If this is the sort of problem setting in which we are at, uh, then we can use this n comma t Shamir secret sharing. So we just set t to be the people at to be the least number of people at which the box should open. N is the total number of people present in the city. And yeah, we'll be done with that. And the key idea behind this n comma t Shamir secret sharing is that if we start with a polynomial of degree t minus 1 to determine all of its coefficients, we'll need exactly t values. And essentially what we do is we generate a polynomial over a field f of x. So we generate a polynomial, let's say f of x of degree t minus 1. And we suppose we generate n values of that polynomial at n different variables. Like suppose we take f of 0, f of 1, suppose we take f of 1, f of 2, f of 3 up to f of n, these n different values, and give one value each to every citizen. There are n citizens in the city. So we give exactly one value to one of the citizens. So every citizen now has one value which is different from other citizens. Like if first citizen has f of 1, second has f of 2, third has f of 3, and nth has f of n. And now if we want to, and suppose the box only opens when you know the exact polynomial f of x, and otherwise the box does not open. So to determine the polynomial, so to open the box, and since the polynomial was initially of degree t minus 1, we'll need t people to come together at least so that the box should open. And if t people come together, then essentially we have t different values. So we have t different values, like different t values of polynomial over t different like variables. Like we have f of 1, f of 2 till f of t, let's say. If first two tth people come together, then we have a value f of 1, f of 2, f of 3 till f of t. And now we have t different values. So now we can actually find out the coefficients of the polynomial by solving certain equations. And that's how essentially we'll be able to obtain the polynomial now. So yeah, and now since we have obtained the polynomial, we can open the treasure box. So at least t people should come together uh, to open. So more than t people can also come together because then also we'll obtain the same polynomial, right? So more than t, if even if more than t people come together, the solution for the equation will still be the same. So that's why if at least t people come together, then we'll be able to obtain the polynomial and hence open the treasure box. And this is what we call the n comma t Shamir secret sharing scheme. So yeah. So yeah, this was it what I had for today's summary session. So you can consider it as a brief overview of all the 12 sessions, not an exhaustive overview, but just a very brief overview. And you can also think of this as some sort of a cheat sheet, which you can refer to, which contains uh, not all, but quite a lot of main concepts which were covered in the over the span of 12 weeks. So yeah. So this was all I had. So I hope you guys enjoyed my problem solving sessions for over these 12 weeks, and thanks for like bearing with me over these 13 sessions, essentially the 12 problem solving ones and this 13th summary session. So yeah, so it was fun interacting with you guys, and yeah, so this is last goodbye for this course. So since I believe since it's a bit late at night right now, so that's why no one is present in the session directly. But yeah, to the YouTube audience, thanks for watching, and yeah, so all the best for the NPTEL exams which you have coming up. So yeah, uh, goodbye guys, and thanks for watching.